Hi everyone, this is Mr. Bowman, and in Chapter 10 we are going to talk about comparing two population parameters, either through confidence intervals or hypothesis testing. So to start out with, we're going to talk about comparing two population proportions. And what we want to do first is get some understanding of how the sampling distribution of a difference of two sample proportions behaves. So what we're going to do is we're going to start out by exploring this sampling distribution, the sampling distribution of the difference of two sample proportions. So we're going to create this scenario, and in this scenario, let's start with two populations. Let's assume we know the population proportions, and let's assume that we have two large high schools, each have over 2,000 students. So here's our scenario. At school 1, 70% of students did their homework last night. So we are treating 70% as the population parameter. Only 50% of the students at school 2 did their homework last night. We're treating 50% as the population parameter for school 2. The counselor at school 1 takes a simple random sample of 100 students and records the sample proportion P1 hat that did their homework. School 2's counselor takes a simple random sample of 200 students and records the sample proportion P2 hat that did their homework. We want to look at the sampling distribution for the difference of sample proportions. So think about what each of those sample proportions means. From each of those schools, we could take lots and lots of different samples of size 100 and size 200 respectively. When we do that, we are not going to consistently get the same sample proportions, P1 hat and P2 hat. So we treat those sample proportions as random variables, and therefore we treat the difference of those two sample proportions as a combination of random variables. And it's been a while since we've talked about combining random variables, but when we talked about combining random variables, we talked about finding the mean and the standard deviation of those new random variables. So since we know that the mean for the sampling distribution of sample proportions from high school 1 is equal to the mean for population 1, and the sampling distribution of sample proportions for school 2 is equal to the population proportion for school 2, the mean of the difference of the sampling distribution of sample proportions is equal to the difference of the means. In other words, the mean of this new sampling distribution, P1 hat minus P2 hat, is equal to the mean of P1 hat sampling distribution minus the mean of P2 hat sampling distribution, which is equal to population proportion 1 minus population proportion 2, which tells us that the sampling distribution of the difference of sample proportions is an unbiased estimator of the true difference of population proportions. So the next thing we'd like to talk about is the standard deviation of this sampling distribution of the difference of sample proportions. And if you recall, when we combine random variables, we add the variances, but we can only do that if the two random variables are independent. So for now, we're going to assume that the two random variables are independent, but we're going to talk about how we check that condition in a moment. So we can add the variances. Well, the variance is just the standard deviation squared. So if you recall, for the sampling distribution of sample proportions from school 1, the standard deviation is the square root of P1 times 1 minus P1 over N1, but when we square it, the radical is going to go away. Similarly, the variance for the distribution of sample proportions from school 2 is going to be P2 times 1 minus P2 all over N2. So that's our variance. Again, we're assuming that these two random variables are independent. So the standard deviation is going to be the square root, or the positive root, of all of that. 1 minus P1 over N1 plus P2 times 1 minus P2 over N2. And this formula is actually on your formula sheet for the AP exam. What must be true about the random variables in order to be able to add their variances? They must be independent. So now, like we have in the past, we know the mean of the sampling distribution, we know the standard deviation of the sampling distribution, and if the sampling distribution is approximately normal, we can do normal calculations. So what turns out to be the case, and if you want to see the demonstration, just ask me or Miss Harding to do it for you in class, is that if the sampling distribution for P1 hat and the sampling distribution for P2 hat are both approximately normal, then the sampling distribution of the differences is going to be approximately normal. Well, what makes, or how do we check for normality of the individual sampling distributions? Well, we use the large counts condition, and the large counts condition comes down to checking N1 times P1, N1 times 1 minus P1, N1 times P2, N2 times P2, and N2 times 1 minus P2. And if those are all at least 10, then both of those individual sampling distributions will be approximately normal, in which case the sampling distribution of the differences will be approximately normal. So here's a summary of the facts about the sampling distribution of the difference of sample proportions. The shape, when all of those N1 P1s and N1 times 1 minus P1s and etc. are at least 10, the sampling distribution of the differences is approximately normal. The center, the mean of that sampling distribution, is the difference of the two population proportions. And the standard deviation is given by this formula right here. So let's talk about this standard deviation situation. What do we need to calculate the individual standard deviations? And what do we need to be able to assume that the two random variables, P1 hat and P2 hat, are independent of each other? We need to meet the 10% condition for both samples individually, and we need to be able to justify that the two samples are independent of each other. So that is an added condition that you have to check when you're looking at the difference of two sample proportions. So in summary, if we meet all those conditions, we have an approximately normal sampling distribution for the difference of the sample proportions. It has a standard deviation given by this formula, which is on the AP formula sheet, and it has a mean equal to the difference of the two population proportions. So we are going to assume that we meet all the conditions for our two schools example, and we're going to use that scenario to do some calculations. So suppose that the two counselors from school 1 and school 2 meet to compare the proportions of students who did their homework last night, and they find that the difference in the sample proportions is 10%, P1 hat minus P2 hat. In other words, the proportion that did their homework at school 1 in the sample is 10% higher, or 0.1 higher than the proportion from school 2. Find the probability of getting this difference or less. So really what we're doing here is we're working off the sampling distribution that has a mean equal to P1 minus P2, and if you recall from the example, P1 is assumed to be 70% and P2 is assumed to be 50%, which is a difference of 20%. In our example, we got a difference in sample proportions of 10%, so that would fall below the mean here. So P1 hat minus P2 hat is equal to 0.10. And we want to find the probability of getting this difference or less. So we're finding this shaded region down here. Essentially what we're doing is we're finding a z-score because we know that the distribution is approximately normal, and calculating that z-score would be the value we obtained minus the true mean, 0.20, over the standard deviation. And again, we're assuming that we know the population proportions, which isn't entirely realistic. So in our calculation here, we're going to have 0.7 times 0.3 over the sample size from school 1, which was 100, plus 0.5 times 0.5 over the sample size from school 2, which is 200, and that gives us a z-score of negative 1.73, and the shaded area is going to be the probability that P1 hat minus P2 hat is less than or equal to 0.10, given that the difference of the two population proportions is really 20%. Basically, we're calculating a p-value, and the p-value is 0.0420. That's equal to that shaded region. So if you got a p-value of 0.0420, if you were doing this as a hypothesis test, does that probability give you reason to doubt the counselor's reported difference of 0.2? So, well, if the true difference is 0.2, the probability of getting a sample difference of 0.10 or less is only about 4.2%. So, since that's unlikely to happen by chance alone, it would suggest to me that the difference in the two population proportions, the true values, is actually less than 20%. All right, what I would like you to do right now is pause the video and work through this check your understanding problem. When you're done working through it, unpause the video and I will go through the solution with you. All right, so the first thing we're going to do is we're going to check the shape of this sampling distribution, and if you do that, you will see that N1 P1, N1 times 1 minus P1, N2 P2, and N2 times 1 minus P2 are all at least 10. Therefore, the individual sampling distributions, P1 hat and P2 hat, are approximately normal. Therefore, the difference in the sample proportions, that sampling distribution, is also approximately normal. The second thing we're going to do is we're going to find the mean of that sampling distribution, and that mean of the sampling distribution, again, based on the assumption that we know the two population proportions, is equal to 0.25 minus 0.35, which is negative 0.10, and the standard deviation, also based on the assumption that we know the population proportions, turns out to be 0.0971. So in the next part, part C, it says draw a picture of the sampling distribution of the difference of sample proportions. Find the probability that P1 hat minus P2 hat is less than or equal to negative 0.02. So my work's a little bit sloppy here, but we're finding a z-score, negative 0.02, minus the mean of the sampling distribution, negative 0.10. Be careful, you are subtracting a negative there. Divide by the standard deviation, you get a z-score of positive 0.82. You should draw a picture of these things to make sure it makes sense. Here at the center of our distribution is our mean of our sampling distribution. Above that, because negative 0.02 is larger than negative 0.10, is the difference in our sample proportions, and we are finding the probability that the difference in sample proportions is less than or equal to negative 0.02, so we're finding the area on the left that is shaded. That difference, negative 0.02 minus negative 0.10, converts to a z-score of 0.82. The area to the left of that is about 79%. So that's a large p-value. based on the answer to that, would you be surprised if the difference in the proportion of red crackers in the two samples, P1 hat minus P2 hat, is equal to negative 0.02? No. If the difference is really negative 0.10, there's about an 80% chance of a difference in the sample proportions of negative 0.02 or less. The one thing I will tell you here is that you have to pay attention to which one comes first, P1 or P2. It doesn't matter. The only thing that would change is the signs. So your mean, if you did P2 minus P1, would be positive 0.10. The difference in your sample proportions would be positive 0.02, and your p-value would turn out to be the same, and you would still make the same conclusion. The next thing we would like to do is construct confidence intervals to estimate the difference in two population parameters or proportions. So we're going to use this scenario about a Gallup poll and how people feel about the intelligence of men versus women. Who do you think are more intelligent, men or women? To find out what people think, the Gallup poll selected a random sample of 520 women and 506 men. The pollsters showed them a list of personal attributes and asked them to indicate whether each attribute was generally more true of men than women. When asked about intelligence, 28% of the men thought men were generally more intelligent, but only 13% of women agreed. Is there a gender gap in opinions about which sex is smarter, or is the difference simply due to chance? And if there is a gap, then what would we estimate the true size of that gap to be? Comparing parameters from two different populations, like the difference in the opinions of men and women on gender intelligence, is a fundamental idea in statistics, and we will explore this. So, we know that the difference between the two proportions, men minus women, from our sample is 15%, 28 minus 13. But what is the true difference? What is the true difference for all men and women? We're going to construct a 95% confidence interval for this difference, and confidence intervals always have the same basic structure. We take the statistic plus or minus the critical value based on our level of confidence times the standard deviation of the statistic. So, verify that we meet the random condition. Both samples were stated to be random. We're good with that. Independence. Be careful about this one. You need to check this 3 times. You need to check it using the 10% condition for each sample. Then you have to check and see if it's reasonable that the two samples were independent of each other. So in this case, they took a random sample of 520 women and 506 men. We're going to assume that those populations are each at least 10 times larger than their sample sizes. Now, how do we go about justifying independence between the two samples? It seems reasonable that if they were both randomly selected, that they are independent of each other. We don't have any other information about, for example, they did this amongst a particular group of people, like from a particular church or a particular race or things like that. So we have to assume that the two samples are also independent of each other. The normality condition here, we would check by taking our sample sizes times our sample proportions. So in this case, we would take 506 times 0.28. We would take 506 times 0.72. We would take 520 times 0.13. And we would take 520 times 0.87. And you can verify that all of them are at least 10. So we can assume that each of the individual sampling distributions are approximately normal, and therefore the difference of the two sample proportions is also approximately normal. So to construct our confidence interval, we need to calculate a standard deviation. But that would mean that we know the individual population proportions, which we don't. So just like we do for single proportion confidence intervals, we move to the standard error and we use the sample proportions in our standard deviation formula. So how does that calculation work out? The calculation basically goes like this. We are going to, so how does that calculation work out? We are basically going to construct this confidence interval, and the formula is going to look like this. Our statistic is going to be P1 hat minus P2 hat plus or minus our critical value. It's a z distribution because it's proportions times the standard error. So P1 hat times 1 minus P1 hat all over N1 plus P2 hat times 1 minus P2 hat all over N2. So a 95% confidence interval for our situation would go like this. 0.28 minus 0.13 plus or minus. For 95%, the critical value for z is 1.96 times the standard error, 0.28 times 0.72 over sample size of 506 plus 0.13 times 0.87 over a sample size of 520, and that would be the work you have to show. And our confidence interval, if we were to then go to our calculator, which I will show you in a moment, is going to be 0.1014 to 0.1986. So remember, order is important when you're taking differences here. So when we interpret this, remember that we did men first and women second in our difference here. Be careful when you're interpreting these confidence intervals. They can be a little bit tricky. So listen carefully, rewind this, replay it if you have to. This confidence interval interpretation is going to be a statement about how confident we are in the true difference, the difference in the population proportions, and order is important here. We took men minus women. We could have easily taken women minus men. So our interpretation would go something like this. We are 95% confident that the proportion of men who feel men are more intelligent than women exceeds the proportion of women who feel that same way, men are more intelligent than women, by anywhere from 0.1014 to 0.1986. Just in case anybody was confused by that, I want to go through that again. That interpretation of that confidence interval would be, we're 95% confident that the proportion of men who feel men are more intelligent than women exceeds the proportion of women who feel that same way by anywhere from 0.1014 to 0.1986. Remember, these interpretations are based on our level of confidence, and they are statements about what we feel about the population parameters, in this case, the difference in the two population parameters. So let's summarize this process. The process for the difference in estimating the difference in two population proportions is called a two-sample z interval for a difference of two proportions. The formula is given by this right here, which is not on your AP formula sheet, but parts of it are. What do you have to check? You have to check that both samples were randomly selected. You have to check the normality of both individual sampling distributions. And you have to check independence in two ways. You have to check that the subjects within each sample are independent of each other by checking the 10% condition within each sample. And then there's an additional condition for independence, and that is checking to see if it's reasonable that the two samples are independent of each other. Obviously, there's built-in technology in your calculator to do this, and this is called the 2PROP-Z-int, and there's a 2PROP-Z test, and I am going to show you in just a minute with this particular example how to do that. Okay, I am going to show you how to use your calculator to do a 2 proportion z interval and a 2 proportion z test. I want to point a few things out here, so please pay attention to this because there's a format issue with the calculator that if you don't get this right, it's not going to work for you. So first thing we do is select stat, we go over to tests, and we look for, we're going to do a 2 proportion z int first. So scroll down until we find the 2 prop z int, 2 proportion z interval. Select that. Just like 1 proportion z interval, we have to put the number of successes in each trial. So in this example, we were not given that number. What we were given is that 28% of men thought that men were generally more intelligent, and 13% of women agreed with that. So we're going to have to take 0.28 times our sample size for men, which was 506, and we do not get a whole number. So what are we going to have to do here? We need to round to the nearest whole number, 142. If you don't do that, the calculator will not do this for you. It will give you an error. So our sample size for men was 506. For women, we're going to do the same thing, and it was 13% of 520 women that agreed with that statement. So we're going to let the calculator find that number for us. We're going to round up to 68. And this is going to change our results slightly from what we would get if we did it by hand. But if you're going to use a calculator, you have to do this. Sample size 520, level of confidence 0.95, and we're going to calculate this. And I and the College Board will accept those slight differences. You will see sample proportion P1, 0.28 approximately, sample proportion P2, 13% approximately, but that calculates our confidence interval for you. If you are going to do a hypothesis test, you'd have to deal with the same issue, and we will come back and talk more about that. But a 2 prop z test, basically we'd have to have our sample, our number of successes in there, which nicely transferred over. And let's say we do a 2-sided alternative. We're basically saying that we believe that the 2 proportions are not equal, and we can calculate this, and it would give us the z-score, the p-value, the sample proportions, the sample sizes, and so on and so forth. All right, I know this is getting to be a long video, so this is the last thing we're going to do. What I would like you to do is pause the video, work through this example. When you're done, hit play, and then I will go through the solutions with you. Okay, we checked both samples were randomly selected. They were. We checked normality of both sampling distributions, n times p1 hat, n times 1 minus p1 hat, and 2 times p2 hat, and 2 times 1 minus p2 hat. All of them are at least 10, so both sampling distributions of sample proportions are approximately normal. Therefore, the difference in the sample proportions, that sampling distribution, is also approximately normal. Both samples were taken without replacement, and each of the samples is reasonably less than 10% of their populations. The samples were randomly selected, so it seems reasonable that the 2 samples were independent of each other. Notice, again, that there are now 4 conditions you have to check. The added check, the different check to make sure that it's reasonable that the 2 samples are independent of each other. When you construct the confidence interval, you could do it the way I did it, 0.47 minus 0.73, or you could reverse it. The only difference is going to be that instead of getting the confidence interval that I got, you would get a confidence interval that went from positive 0.223 to positive 0.297, but you would still interpret it the same way. So you have to pay attention to which sample came first in your confidence interval. So how do we interpret this? We're 95% confident that the proportion of teens using social media exceeds that of adults by anywhere from 0.223 to 0.297. Notice, even though my confidence interval was entirely negative, the way I interpret that, it clearly states that we're confident that the proportion of teens using social media exceeds that of adults.